Hi, this is Mrs. James, and this is my summary of the lesson that I did in class covering the three classic problem types in two-dimensional motion. First problem type, things on ramps. They may be sitting still, they might be sliding down the ramp, they might be being pulled up the ramp. Number two, things being launched. Maybe they're being kicked, maybe they're being shot out of a cannon, maybe they're being flicked off of a tabletop. Number three, things that are being pulled or pushed at an angle. If you're having a hard time imagining this, just think about a wagon. And if you're pulling little kids in a wagon, that handle of the wagon is probably not going straight out in front of the wagon. It's probably a little bit of an angle. That's what I'm talking about here. Alright, so we're going to start with things on ramps. So here's the basic scenario. Of course, this is going to change based on the details of the specific problem. I'm going to talk about a box on a ramp that's sliding down the ramp. So the box is on a ramp, it's at an angle of 30 degrees above the horizontal. And of course, in a real problem, I have to give you lots of other information, like the coefficient of kinetic friction and the mass of the box and those sorts of things. Alright, so there's our box sitting on the ramp. There's our 30-degree angle. Basic setup for this problem, draw your axis, so your coordinate system. Draw them so that the x-axis is the surface of the ramp. There's our force of gravity. So that's the primary force that's happening in this particular problem of the box sliding down the ramp. And I've put in here my y component of the force of gravity and my x component of the force of gravity. Normally when we draw a free body diagram, we put them all coming out of the central point. So this is where our center of gravity of our system. But you know by now that if we're going to be solving this problem, we're going to tip to tail these vectors, and then our resultant vector goes from the tail of one vector to the tip of the other one. So here's our force of gravity, here's the y component of a force of gravity, here's the x component. Add in our force for kinetic friction and our normal force. A few more things I've added here. One, if this angle is 30 degrees, then this angle is 30 degrees. Here's our right angle. I want to point out here that our normal force is the same size as the y component of our force of gravity. Normal force, as always, is perpendicular to the surface. So you want to keep this in mind. Force of gravity is not perpendicular to the surface of the ramp. It is perpendicular to the flat surface itself that's right here. Alright? And again, this is equal to this arrow. This normal force is not equal to this arrow. Well, let's talk about y for a minute. You may have gotten a paper from me in class. The first page asks you to draw this diagram. The second page asks you to identify what the x and the y component of the primary force were doing. And the third part asks you to come up with the sorts of things that I might ask you to solve for in a problem. Let's talk for a minute here about what's being accomplished by the y and the x component of the forces. The y component of the force is keeping the box pressed against the ramp. That's why these two vectors are the same magnitude, opposite directions. The entire force of gravity is not keeping the box pressed against the desk, which it would be happening if the box was sitting on a flat desk. Since it's an angle, only the y component is doing that. The x component, let's move it back up here where we had it earlier, is now our applied force that's moving the box down the ramp. So let's think about some of the problems I could ask you to solve. I could give you certain information and I could ask you to solve for other pieces. For instance, what's the acceleration of the box? Alright? And show you here that our friction force is smaller than the x component of the force of gravity. Therefore, the box would be accelerating. Alright? If they're the same size, it would be moving at a constant speed. Or I could give you that, and I could ask you to solve for the coefficient of friction of the box and the surface that it's on. Or I could go a step farther and give you time and say, how far will the box move during this time? So you do two parts there. You have to find the acceleration, and then you have to find the distance. Or I could ask you what the final velocity of the box is after a certain amount, distance it's traveled. So in other words, once you solve for the basic information that comes out of this setup, I could then make you move forward into any of the kinematic equations that we learned earlier this year. Alright, here's our second classic problem. A football is being kicked at an angle of 30 degrees above the horizontal. Notice I do not have my coordinate system tilted this time, straight up and down. There's my kick. So I'm going to refer to this as my applied force. And there's my 30 degrees. Alright, here is my x component of my applied force and my y component of my applied force. And again, normally in a free body diagram, we show them coming out of the middle of the system. But in this particular case, because, as you know, we're going to be using some trig here, I've moved it parallel out so that I'm tip to tail. My resultant vector, again, is lined up. There's a right angle. There's our 30 degrees. Usually in these particular problems, we ignore friction. So these problems are generally called projectile motion problems. And again, usually we'll ignore the air friction in that kind of problems. Alright, we also have a force of gravity and we have our normal force. Let's look at how I have this problem worded before we talk anymore. A ball is being kicked. So this is the point in time that the foot is in contact with the ball. The ball has not left the ground yet. That's why we have a normal force that's offsetting our force of gravity. Of course, once the ball was actually in the air and had moved, some of these errors are going to go away. If it's flying through the air, there's no more normal force. Once it's left your foot, this applied force would be gone. So would the y and the x component, and all we would have would be the force of gravity. So again, once the ball had left your foot, this is gone, this is gone, therefore this is gone, and this is gone, and this is gone, and this is gone, and this is gone. So that's the object once it's actually in the air. Alright, what is often done with these particular problems is that we're not even looking at forces at all, we're looking at velocities. Because remember, vector arrows can be used for any vector, not just force but also velocity or acceleration. So here we have the velocity of the kick, or the velocity of the ball that the ball is traveling at some point in the future. We have a y component, we have an x component, the acceleration of gravity, 9.80 meters per second squared, in the negative direction, and the y component of the vector is only pointing upwards when the ball is moving upwards. When the ball is moving downwards, like so, at some later point in time, then of course the y component is going to be pointing down. X component will continue to move forward. I have an entire different recording talking about those particular problems you can look up if you want to. So let's go back here for a minute. What in this particular type of problem are our applied force in the y and the x direction doing? Well, this one is accelerating the ball upwards. This is accelerating it forwards. What kind of problems could I ask you to solve for this? Well, again, these problems often show up not as force problems but as velocity problems. So we could be asking questions such as, how high does the football go? How far does the football go? How long does it take the football to reach its highest point? How long is the football in the air? Those sorts of things. Alright, now here's a picture of a box being pulled forward by a rope. There's an angle of 30 degrees above the horizontal. Again, if you want to try and picture this, picture pulling a wagon. And sometimes the object is being pushed. It looks a lot like a picture that I just showed you for the football being kicked. A few pretty important differences. Here's our applied force, which we might even want to refer to as a tension force instead of an applied force. Means the same thing, we just often use the word tension if there's a rope that's involved there. Here's our y component, here's our x component, 30 degrees, right angle. Notice here that our force of gravity and our normal force are not the same size though. Alright, even though this object is sitting on the ground, these two areas are different sizes. Let's take a look at what's going on here. The two upward forces counteract the force of gravity. So our applied force in the y direction and our normal force together are the same size as the force of gravity pulling down on the box. This makes sense. These down forces and the up forces have to be balanced because the wagon or the box is neither accelerating up into the air or crashing down through the floor. So those two things have to be balanced with this thing. So in other words, the larger the y component of the applied force, the smaller the normal force is going to be. Put them back where they originally were. So we're trying to calculate our normal force. We need to know the y component of our applied force. And normal force should give you some indication there's probably going to be friction involved, so I could be adding here force of friction, opposing motion, and I could ask you all sorts of problems about this. What's the acceleration of the box? Then I could give you additional information, such as I pull it for 20 seconds, how far has it gone? Or after a certain amount of time, or after a certain distance, what's its velocity going to be? Those sorts of things. Alright, hope this has been useful information for you. You can listen to this at your leisure. Pause if you need to. Go back and look. You can look some information up in Chapter 5 and Chapter 6, also of our textbook.